Yeah, so our talk is called Demand-Driven Architecture. Hopefully by the end of the talk, this new bit of jargon will make some sense. So what is this talk about? This talk is really focused on sort of the way the technology space is going, and really clients are really shaping, really shaping the design, the architectural designs we need to make when we're building systems. And the way that they're shaping this design is that every day there are more and more clients. When I started at the New York Times in 2010, the iPad had not yet been released, and it had just come out. I worked on the midterm elections, and we wrote our very first iPad-optimized application. It had to be different. The sort of touch-based presentation was quite different from what we were doing on the desktop. Now this just seems like it's just the way things are, but it wasn't that way, and that was only 5 years ago. The Internet of Things is really happening, right? The next thing are even smaller devices, and these smaller devices are fully capable things that are connected to the Internet. But the problem is, if you're going to design such a system, right? And we encountered this firsthand when I was at the New York Times, and I'm sure you guys have similar stories. Like, how do you write a backend or a service that can meet the demands, the varying demands of each client? Different clients need to present different kinds of information. How can you successfully serve all these heterogeneous needs? So, I would say that the mainstream okay, great. I'm going to just turn this off. Sorry about that. Okay, so I would say that best practice, the thing that you'll hear people talk about quite a bit, is they say, well, build a REST service. And I'm sure all of you have done this, so I'm not going to spend too much time on it. But generally, when you build a REST service, you define some logical resource. A client requests that logical resource. But really, it doesn't take very long before you hit lots of problems. Because what will happen is somebody's writing a rich mobile client, and they realize that not only do I need this one logical resource, there's actually there's an implicit join. I actually need some other logical resource, right? It doesn't actually belong at this resource. I want these resources, but I want it joined with some other thing. And people add query parameters, and then eventually the URL is this ridiculous long thing. And then the back-end team's talking to the front-end team, and they say, okay, what are we going to do? Are we going to keep bloating our resource? Are we going to keep changing our back-end queries and sort of polluting this logical resource? Or are we going to force clients to make multiple requests? Which, back when we were all running on high-powered desktops, that was okay. But your mobile phones have very serious latency problems, right? They're on these very low bandwidth, mobile networks, and really getting them at making those clients request multiple things. It's just not great. It's not great UX, right? The app's going to get slower. So what do you do here? So you're either going to inherit incidental complexity because your back-end sort of endpoint is doing too much, or you're going to incur mobile client latency. And this is what I would say the sort of traditional best practice is like supply-driven architecture, the opposite of what we're going to recommend. Because basically the way these systems work is that somebody says, this is what our endpoint has. So basically you can have anything you want as long as it looks exactly like what we've guessed all clients in the future will need, which is not going to work. And then there really are, what happens, you have engineering team issues. People are so stuck to the way that they're doing it, they don't really think about, oh, most of our problems are arising from this architecture that we've chosen, right? So the front-end guy wants to add, or lady, wants to add one new field. But that field isn't present in the table, so they have to go talk to the person to change that, or change the query, or add a new endpoint. And then suddenly, it takes 2 weeks before the front-end person gets to see the one little thing they wanted to see in their iOS app. And then this is really, it's not scalable, right? Eventually, you're going to have enough different kinds of clients that it just stops working. And it's not, I mean, even though Kovas and I here are presenting one particular strategy, lots of companies are actually coming to this realization. Yeah. Okay, so REST services, people's REST services end up looking a lot like this. This is a great little image from Howl's Moving Castle, the Miyazaki film. What happens is your backend ends up looking like something that's it's just a monster, right? And it doesn't actually do any one thing well. There's just an accretion of things that this team added this thing to this endpoint, this person added this thing to that endpoint, and it's just a big mess. Most mature endpoints, REST services, this is where they end up. So what's the actual problem, right? It's not really about REST. We're not up here to say you should never use REST or REST is fundamentally flawed. It's just there's some assumptions about a REST-based service that are deeper than REST itself that are the source of the actual issues. And really, fundamentally, it's because we're pretending that we can predict the future, right? Nobody actually can, but you're pretending that you can. We can't predict what future clients will need, and we have to accept that. And the other thing that's happening is that if you have N teams working on N different clients, Android, iOS, and then soon you'll have an iWatch team, right? You can't put all these clients into lockstep, right? So there used to be this previous world where it's like, oh, this is version 1 of our API, this is version 2, right? And it just can't work, right? You can't have everybody moving at the same speed. I mean, if you're at a certain size of scale, maybe if you're Google or Facebook and you have the resources to do this, okay, maybe you can make that work. But I know there are a lot of companies that don't have the ability to really get everybody to move at the same speed. People move at different speeds. Your architecture should accommodate that. The other final thing is that really clients' applications are fundamentally distributed systems. Most of the way that people design apps still have not come to terms with this fact. I mean, you just have to stop pretending. Latency really matters, and you need to design your architecture to account for latency. We'll see more of that later. The funny thing is, this has all happened before, right? There's nothing new here, right? This is an image of old database systems. This is all old stuff. When they first started designing relational database management systems, they solved this problem. They said clients get to specify what they need. It's called SQL, right? You can have N clients. They all have a language that they can speak to the database. Everybody gets exactly what they want. Multiple clients are not locked into the same results, right? REST just throws the whole original great idea that everybody gets to get what they want out the window. And then there's lots of considerations around batching. I mean, a lot of SQL was designed around the fact that we need to do the cost of making the connection and getting the information is very expensive. You need to be able to batch what it is that you desire. Okay, so okay, we're up here saying there's these problems, but what are you going to do about it? Is it possible for an endpoint to provide a restrictive yet expressive query language, right? We're not going to come up here and say you should expose a SQL endpoint to the open internet. That's not what we're suggesting. But we need to come up with something that has some of that power. Can we design endpoints that evolve with clients? How can we actually do this? Not clear yet, but we'll see. And then this is even more important question. Can an endpoint serve multiple tiers of demand from a client? The thing is that most of the systems we design today are heterogeneous systems, right? You have microservices. You have your SQL database. You may have some third-party thing built in that you need to get. So clients need to be able to access some single logical result, even if that logical result is serviced by different aspects of your architecture. And this is something that I think a lot of people haven't thought enough about. So I'm going to hand it off to Kovas to explain demand-driven architecture.
Thanks, David. In this part of the talk, I'm going to describe and demo demand-driven architecture. So at the high level, the problem we have is a problem of managing complexity. The diverse evolving clients are simply a part of the landscape that our architectures have to deal with, part of the problem, as David described. And you can kind of think of it a little bit like this river basin. The landscape has all these detailed local variations, and the river has to adapt to them. All the little complex branches are necessary to achieve the overall goal. And likewise, in our architectures, there has to be some process that takes data from the source and transforms it and adapts it into the local conditions, the local requirements of every single individual client. So the question then is, how do we represent or encode all of this essential complexity? Do we do it as code, or do we do it as data? Do we do it on the service, or do we do it on the client? In this talk, we're arguing that there's tremendous benefit to doing it as data on the client. Data's a lot easier to change. It's also a lot easier to reason about, which means it's easier to automate and optimize with. And clients are really the source of this complexity. We want to keep the complexity sort of encapsulated at the client. We don't want it leaking over into the implementation details of the service. So how do we do that? The big idea is we want to explicitly represent the client's demand as data. So the client, we can't predict what the clients need, so why don't we let the clients tell the service exactly what they need? So the client describes its demand, its overall aggregate demand of everything it needs, and the service fulfills that demand. This is in contrast with REST, where there is no single explicit representation of the sum total of what the client needs. And instead, the client logic iterates, hitting endpoints, potentially hitting multiple endpoints, and has to stitch all that data back up to get the final thing that it actually needs. So representing the client's demand as data is really the big thing, and that immediately buys us two important properties. First thing is it provides us a specific place to capture all the variation in the client's demand. If the client decides it needs a new piece of data, it has a single place, a single data structure that it can change, and no, it doesn't have to change any code. And that variation is also captured on the client. If the client decides it needs a new key value pair from the service code doesn't need to change at all. The variation is captured on the client. Second thing it gives us is an explicit contract between the service and the client, right? This data representation of the client's demand is an explicit contract. So the service doesn't have to make assumptions of what the client needs. It's told what the client needs. And the client doesn't have to make assumptions about what the service is going to return. And that helps us build simpler and more robust systems. So the big idea is relatively straightforward, but there's some nuanced principles that we really need to follow that are about, well, what exactly is this data description of the demand? What properties does it have? What is it exactly? So let's step through these principles before we get to the demo. So the first principle, the top line principle, again, is the clients must exactly specify their demand. And there's a few aspects to this that might not be immediately evident. The first aspect is it needs to specify what information it needs. So the client specifies exactly what information it needs from the service. If the client does not ask for a piece of information, it does not get it. In contrast with REST, the client might receive a payload that could quite well include information it just doesn't care about, right? The service decides to send whatever payload it decides to send, and what's in there is in there, whether the client really wants it or not. The second aspect is just as important, which is the shape of the data. What shape the data is in is extremely important to the client. All the client really wants to do is get a response from the service and then carve it up and pass out pieces of the response to its individual subcomponents and subsystems. The client doesn't want to be responsible for reshaping whatever shape data the service decides to send into the thing it actually needs. So part of the client's demand is specifying the exact shape of the data that it wants from the service. Second principle is composition. In this architecture, we use a simple recursive data structure, a tree, to describe the client's demand. So the composition gives us two important things. First thing it gives us is variation. Variation through composition is an important principle in computer science. It means that we can easily swap out subcomponents or build up more complex descriptions out of simpler pieces. Another thing it gives us is batching. In this architecture, batching is a general property of the entire system, not something special case to specific endpoints or use cases. So the way this works is each subpart of the demand, a subdemand, is itself a valid request. But because we have composition, we can stack all those demands up into a much bigger demand, ship that whole thing over to the service, and get it back as a single request response cycle. The third principle is interpretation. Interpretation lets us further decouple the client from the backend implementation details. It's the thing that sits in between the client and sort of all the internal implementation details of your architecture. So again, the demand is this simple recursive data structure, and when the service receives it, it simply recursively interprets it within the context of its own architecture. So the client doesn't care, and the client doesn't want to specify where the data is, right? The client doesn't care if the data is in a relational database, it doesn't care if the data is in the key value store or computed on the fly by microservices. It just wants to describe what it wants and leave it up to the service to interpret that demand in terms of its own internal implementation details. Also, this is an important hook for satisfying our security constraints. So here, we're sending something a little bit more sophisticated to the client in comparison to just sort of hitting a REST endpoint. And sending something more sophisticated to the service than just we would with a REST endpoint. But because we have this simple data structure, the service can inspect it and analyze it and make sure everything is okay. We can go ahead with this request. We can contrast this with, say, the SQL situation, right? If we're just passing a string, how are we going to inspect and analyze that string? Okay, we can go ahead and parse that SQL string, but the semantics are just too rich. It's just too hard to understand what that, what that's meaning. So interpretation in conjunction with a simple data structure makes it easy for us to understand what the demand from the client is saying, and make sure that everything is safe to execute. So with that, let me move into the demo. So here we have an extremely trivial client. It's basically just a shell. I've already set up a service on the back end and populated it with some data for a very simple sort of contact book application. And our client here is simply a shell that's going to let us specify the demand as a data structure, send it to the service, and then it'll show us the response on the right here. So this data structure here represents sort of the request that the information that the client is going to ask from the service. And it's saying, let's get the context for the app. And then for each contact in the app, give us the following information. In this case, just the first name of the person. So I'll click this, and here we see the response from the service. So the response of the service is in the same shape as the request from the client, except now it's been populated with concrete data, an array with two persons in there with just their first names, as we requested. So in essence, you can think of the demand as just a skeleton that the service interprets and then populates with the data. Let's just take a look at how that looks on the back end and kind of step through what just happened. So again, that's the demand from the client. And now the service is going to recursively interpret it, starting with the context key. In our service, like in many services, we often want to immediately route based on sort of some very top-level information. And that's what we're going to do here. Our service is going to interpret that key as a route and then send the remainder of the demand to a specific context query. And the context query is going to take the remainder of the demand as a parameter, get the context, and then for each contact, give us just the first name. The result gets all aggregated up, and that's what we see. That's what we see here. It's okay. It's okay. Yeah. Okay. So far so good. Let's see what happens. So let's decide. Okay, maybe the first name's not enough. We probably also want to see the last name of these people. Do I need to go and ask someone on the back end to add the last name as the part of the response from some endpoint? No, that's what we don't want to do. All we want to do is change the data at the client and get that as something that we're getting back from the service. Actually, can you do that? Thank you. So I'm going to go ahead and add the last name as something I'm asking. And there we go. Now we have the last name as part of our result. So let's do something a little bit more sophisticated. So we're going to decide, okay, first and last name are great, but we're also interested in the addresses of the person. So let's do this. So this is sort of where the magic happens. We've gotten back something a little bit more sophisticated than the previous examples. The address is not just a string like the first and last name. It's a whole nother level of entity, a whole nother sub-data structure with its own street and city and zip and so on. And this is exactly the situation where in a REST design, we would have been hit with this trade-off. So in a REST design, we would have basically two kinds of resources. We'd have people resources and we'd have the address resource. And in designing the endpoint for this, we'd have to make this decision. Should we just return the people and then make the client come back with another request to get all the addresses for each person? Or should we bloat the response and just go ahead and stuff all the addresses in there? And if we do that, then some other client comes along, and now they're getting information they didn't ask for and doesn't fit their requirements. In this architecture, this problem simply goes away because the client can exactly specify what it wants, and the service can specify that demand. And in doing so, no special case code has to be written to support any particular client at the service. Every client can get exactly what it needs. And there's one more thing that's really important about this example that I'm going to show, which has to do with interpretation. So let me step back to the slides here. So again, this is the sum of our demand right now. We're routing on the contacts key and passing the subquery to our contacts query. And even though we've specified our demand as a tree, we've actually implemented it in terms of a relational database. So on the back end here, we've chosen to use a relational database. There's basically person table, there's the equivalent of address table. For each person, the address points to some entity in the address table. And as our query engine is interpreting our demand, it understands that we're asking for the address of the person and simply automatically performs the join for us. Right? It just inserts that join on our behalf. And the client didn't have, no one on the service team had to go and implement special case code, a special case join to get this done. It just happened automatically for us. And that's great, but the beautiful thing is that it doesn't even matter that we're using a relational database here. This is kind of the point of interpretation, is we could be using anything we want on the back end. As long as we have a process that understands what the client is asking for, it can delegate to the implementation to figure out the details to make it happen. All right, let me show you one last thing. The last thing I want to show you is the property of composition. So far we've simply added, we've sort of extended our demand and at the same level of nesting here, adding the first name, last name, the address. But now let's suppose that we're working on some particular subview, and really all that we care about is the zip code of the address. So how do we go about modifying this query and simply get only the zip code of the address? The way we do that is we use the exact same data structure that we're using to express everything else, and we simply say address zip code. Then we do this, and boom. Now we simply are getting the zip code back for the address. So this is pretty awesome, right? We were able to make a highly specific query that no backend person could have possibly predicted that this client would need. We've iterated on the query 4 times simply by editing this piece of data. And the client is getting back exactly what they need in a single batch. No code was written on the client, no code was written on the service. So let's review our demand one final time. So this is the simple data structure that represents the demand of the client. As far as the client is concerned, it's simply asking for data from the service. when it hits the service interprets this parts of this data structure as it sees fit. So the first part is used to do routing, and then there's a query and a subquery that the service will automatically join together for us. And this all comes back in the shape that the client expects. So just to wrap up what we've seen here, we've seen the client specifying exactly what it needs as data. We've seen that the queries are getting batched. The details of the demand are very easy to modify. We're just changing the data structure. We don't have to ask any service teams to change any code on our behalf. We're even having implicit joins happening automatically for us. And it's decoupled from the service implementation. The client doesn't care that it's in a relational database or whatever strategy the service is using to implement this. These are completely decoupled things. So with that, I'll hand it back to David.
Thanks. So hopefully we have a pretty good picture of what it looks like for a database endpoint. But the thing is, it actually has huge ramifications for the things that we're building, which a lot of people are building graphical clients. Again, whether that's mobile, desktop, it doesn't really matter. This is a game changer because most of what people are doing is they are talking in a REST endpoint, they have some duplicated MVC thing on the client, whether that's Backbone or Angular or Ember, which is replicating, the whole idea of something that the backend already does, again on the client. And this is all sources of error. Actually, Jafar Hussein's going to talk about an alternate version of this tomorrow when he talks about Falcor. But the idea is that you can bind directly to your remote service. And the thing is, remember, it's really, what's beautiful about this approach, it doesn't matter if it's local or remote. But what this approach gives you is that if it is remote, you can just eliminate the entire traditional sort of model layer on the client completely. And so why is this the case? And how can I make this claim? So user interfaces. User interfaces are fundamentally trees, right? The queries that we've been showing you are tree-based queries. Your application, if you build an iOS application, you have a root view. Then you have children views. The root view makes the request, and it propagates the data all the way down, right? So there's a direct one-to-one correspondence for whatever your UI tree looks like to this query that we've been describing. And we can take it a step further. We can just annotate our UI components with the query fragments. Because we've picked a recursive data structure, we know that these things can compose. And so I'm going to demonstrate this. So graphical clients that talk to traditional REST service, they generally involve error-prone reshaping code, right? Because the endpoint doesn't know what you want. It doesn't know, it can't predict what shape your UI tree has. Every client that's to talk to REST endpoint needs to reshape. So people are writing boilerplate code just to get the data into the shape that they actually need it in. And so demand-driven architecture can dramatically simplify clients simply by just eliminating all that code. That code just disappears. Like all the code you wrote on the back end to serve a client, that's gone. All the code that you wrote on the client to reshape this result that you didn't want, it's gone. So how would we do this? So again, it's actually quite simple. So I can imagine a contacts app in which I have a root view at the root. It's an app view. And it has this query fragment. And it has a blank spot where it says, my child component will supply this. We move down to the contact list view. It has the query fragment that describes all the fields that it needs. And then at the bottom, there's an address view that has just the little piece of data that it needs. Any person on your front-end team, again, Android, iOS, web, it doesn't matter. They don't need to talk to the back-end person to get the data they need now. You don't have to change any endpoints, and you don't have to change any queries, right? The UI gets to specify the shape that it's going to get, and nothing needs to be reshaped. So let's see a quick demo of this. So here I have, this is actually, it's basically what we saw earlier, but I'm using React. I'm actually using React with a library I designed called Ohm. This is actually sort of the next version of Ohm. But here we're taking the result, and we're rendering some HTML elements, a list element, an H2 tag, or whatever. So how is this actually going to look? So let's look at some code here. So this is all in ClojureScript, and that's really neither here nor there. Don't focus on that part, because this will work if you're doing JavaScript. It just doesn't matter, right? All the principles we're talking about port. It's like there's nothing ClojureScript specific about this. I just prefer ClojureScript. Okay, so here I have my root component. My root graphical component is a contact list. Down here, I have this get query contact list, right? So I can say right now, I can say, imagine I haven't even rendered the view. I can ask the root UI component, give me the query you're going to send to the server. Whoops, am I in the right place? Oh, sorry, one second. Sorry. Oh, the Wi. Did the Wi-Fi mess it up? Sorry, one moment. Let me just join this. Software. Thanks. Apologies. Yeah? So annoying. Let me just start this again. Okay, so while that's firing up, let me show the bits of the code that are relevant here. Okay, here we go. So here, what I was trying to demonstrate is that here we have the contacts fragment, and what we do is we say this variable is going to be bound by its subcomponent. And so if we look up here, the contact says I'm going to need the person's first name, the last name, and I'm going to need their telephone number. And I've commented this part out where we ask for the address info. But if we look up here, the address info says I'm going to need the address, street, and the city, and the address. And again, so what I'm saying is that these are static methods. So unlike most UIs where you actually have to instantiate the components to even run the query, this was an idea taken from Facebook's Relay, where if there are static methods on the class, we can ask the root class, run your static method, give us the query, and that will invoke all the other static methods of the subcomponent classes, and that can give us, before we do anything, before we instantiate the UI, we can get the data, right? So this whole loading thing that you're used to, we don't have to do this. We can just get all the data all at once. And I'm not sure, I might have to skip this demo because I think there's just too many network issues here. I don't think so. No. It's not going to work. Yeah. I don't know. Let's move on. Sorry about that. I was hoping to show this in action, but I don't think it's going to happen. I think the issue is that it's just not connecting, right? Let's just move on. Okay, so I wanted to show that demo, but sorry, it's not working at the moment. But so what was I going to demo? Was that when I ran this query, the same queries that Kovas showed, where it was data oriented, I can actually ask the UI components, give me that same structure, because I've annotated all my UI components to do this. And again, so even though we couldn't connect and I couldn't show the live demo, it's still the case, right, that this, if I examine this, So if I examine this, just so that you can see that this happened, when I re-rendered, this was actually rendered by the code that I wrote. Here you can see it did happen, right? This is, if you're familiar with React, it fetched the data in exactly the shape that I needed it, and then it rendered the thing. I didn't write, if you look at the code, I didn't write any shaping logic, right? No shaping logic was written. I never had to write any models, right? No models. My model is the back end. That model was already written. There's no need to repeat that at the client. So caveats. So it doesn't mean nothing that we've talked about doesn't mean no back end. In fact, what's kind of beautiful about this approach is that on the back end, instead of having a lot of incidental complexity, you just focus on the things that actually matter for the back end. So things like security. Security is just as important as it ever was. And in fact, you have to be a little bit more vigilant here, because we do have, again, a very restrictive yet powerful and expressive query language. Fortunately, it's simple data, and it's easy to traverse, and it's easy to manipulate because it's simple data. It is not an arbitrary query language. Routing is important, right? So you may have, your service may have different tiers, and so you're going to probably have to say, this key goes to this route. So this key talks to our database, this key talks to a microservice, so there's still the concerns of routing, except it's a more sophisticated kind of routing, right? Normally, people are only routing on fragments of a URL. Now we're routing on a rich data structure that needs to be populated. Caching is also important, though part of what we're talking about here is that this is a design for rich applications that aren't just web pages, right? For any application where you're building something rich, this is superior, and you couldn't do any sophisticated caching anyway, right? It's an application in which all your clients need something dynamic, they need something unique. And in this case, caching on the client works great. And again, if you look at what the Relay Facebook guys are doing, and Jason Graff and Falcor, you'll hear them say this quite a bit. So you can also level up. What's beautiful about this is that if you pick a system that is already designed to work in the way that we've described, there's a lot of extra things you can do. One of these is DeTomic, and I'll talk about Relay and Falcor as well. DeTomic, it's kind of interesting. 3 different systems came up with the same idea all at once. DeTomic has something called the pull syntax. So the syntax we were showing you for our query, it's just the DeTomic pull syntax. And we picked it because we knew we could take that syntax, get the fragment that's the query that we want to run, and just run it against the database. There was no extra work for us to do. It also has a great caching story. So you can basically have your storage, and then you can have n peers in front of the storage, and they're all effectively caches. So it's a great caching story. So it's even better than what you described. So you would get effective caching at the service level, not just the clients. It's also an evolvable schema. So nothing we were showing was, it's not a document store, right? Document stores, the reason people hate document stores is they're not relational. You can't write relational queries. You have some document structure, and you're stuck with it, right? You're stuck with whatever document structure you picked. It's not an evolvable thing, not in the way that SQL is. So DeTomic gives you a relational system, and you can evolve the schema, no migration. So you can even do things like, I'm going to add new properties to this entity, and all the old clients that don't care about that weren't asking for it, and they're not affected, right? But the new clients that need it, boom, they got it. So this is the whole idea of you can have n clients being developed, and they don't have to be in lockstep. DeTomic has really cool stuff where you're like, you can query arbitrary points in time. If you're like, I need to show my client the exact same UI view that they saw last week for some reason. So DeTomic, you just get this for free. It's just a property of the system. And clients can also trivially receive change sets, which is huge for any rich client application that has any collaborative element, where there's other operations from other users. You can be at time T50, and then time progresses to T100. You can say, give me every delta. You can just ask the database, give me every delta for this user in this time span. And it's just out of the box. Relay GraphQL. So again, this is not just DeTomic. Facebook has a new thing for React called Relay GraphQL. The exact same concept. You have a composable query syntax. It's a layer over React. What's interesting about Relay and GraphQL, Relay and GraphQL, they have arisen. It's arisen out of Facebook's fundamentally monolithic architecture, right? They want to pretend that there's some MySQL-like thing, and they're going to run graph queries over it. There's one logical database. GraphQL is meant to run directly against this logical database. And again, so it allows them to build, they're already building apps. They've already shipped an app using Relay and GraphQL. So they're already doubling down because it just eliminates a bunch of complexity for them. Very cool. If you haven't watched the Relay GraphQL talks, I highly recommend it. It's excellent. But they're not the only people with this idea. Netflix announced something earlier this year called JSON Graph and Falcor. It's the same thing. This talk is about extracting out the principles from these different systems and saying there is a principle here, and that's demand-driven design. Netflix eliminated 90% of the networking code, right? So they had all these REST endpoints, and they were able to just throw them all out when they switched to Falcor and JSON Graph. JSON Graph allows them to write queries as recursive JSON data. And Falcor is the router. It's the thing that actually routes all the keys to all the microservices that they have. So that's fundamentally different from Facebook, right? So the same idea works regardless of whether you have a microservices-based system or a monolithic-based system. It doesn't matter. And Netflix has this huge problem, which I just described, right? They're serving everything from set-top boxes to your iPhones. Okay, so just a brief recap. The pace of client innovation is only accelerating. I think people are well aware of that. Demand-driven architecture guides us towards evolvable systems. I think this is one of the biggest problems that we have, is that we attempt to predict the future, we can't, and then you've locked yourselves into a bunch of decisions that you can't change. And a lot of this talk is just laying out a framework for how could you design an evolvable system. And you can remove all this incidental complexity from client and server by meeting on simple data. I mean, that's really if there's any takeaway, is if you meet on simple data, you're going to win. I mean, one of the problems with REST is that you're meeting on a string, right? That's the fundamental unit of REST is a URL. Like, that's it. That's one path into your backend. By picking a more rich data structure, you can basically represent multiple paths into your backend. So here are some references. Our slides will be up at some point. But these are all things worth looking into. If you're curious about, again, this is not just one idea. A lot of people are having the same idea right now. And I mean, we're definitely convinced that this is the way things are going. We're probably running out of time. And if we have any time for questions, we'll take them now. They're not mutually exclusive, right? You could imagine, for example, every product, right? You gotta write web pages, right? You have there's some parts of your service that are best served by things that REST is great at, but there are probably places where you're building a rich client, and your rich client is probably better served by something like this. So it's a good question. So how do you do posts? And so this is the part where it's like it just depends on how you want to build your system, right? Once you have a simple data-oriented thing, lots of wins. In the case of DeTomic, it's quite simple. In DeTomic, it's kind of nice in that you don't need CRUD. In DeTomic, you can't erase information anyway. So there's only two operations. You can assert something, which is either creating it or updating it, or you can retract something. There are no other operations. So in a DeTomic-based system, I'd be like, oh, I can assert something, or I can retract something. And both of these would happen via post. It would just be, this is an assertion or retraction.
Yeah, because what I meant is there anything there that allows you to send stuff back?
Not in the query syntax. You're totally correct. Not in the query syntax. But this is not a hard thing to do. You add some other thing which says, I'm sending update information here. Yeah. So there are other best practices that aren't going to change, is the answer to that question.
Can you suggestions for how to quell the streams of the DBAs about the unpredictability of load on the database?
So it just depends. So that's assuming you've gone the direction of I'm going to map this to a database, right? So there is a challenge for systems that use Relay, right, and GraphQL. You're going to have to build a lot of custom indexes. Which is also why we decided to come up here and show it with DeTomic, because DeTomic the database solves that problem for you. But again, it doesn't preclude. For example, if you already have a microservices thing set up, you can do it that way. It totally works.
So I'll just throw in a few more comments on that. One of the things that we didn't quite dwell on, but I think is quite helpful is, it's very easy. It's much easier in this setup to trace where things are coming from, right? It's not like you got some random client hit an endpoint and then somewhere in the code spaghetti, there's some joins happening somewhere. Because you have the whole thing as data, you can analyze more readily, which client might be causing load, what request patterns are coming in. It's all much easier to inspect and analyze and sort of trace through to the root of the problems. And just to sort of expand on what David said, yes, sort of there's this greater power of how clients can request data, and perhaps there's these joins happening that someone may not have predicted. And this sort of raises another question of, well, what other parts of our architecture are unnecessarily coupled? Is it necessary for all clients, is it necessary for all kinds of applications to be serviced by this same single database? Or can you have something more like a DeTomic model where you can have someone's long-running query satisfied independently of someone else's short-running query, and separate those out because just the nature of the architecture allows clients not to step on each other in yet another way.
How rich does the query language ultimately get? Because if I want to give the client what they want, if I take a slightly more complicated article of contacts, orders, products, I want to know all the yellow shirts that Bob bought between a certain date range. Now I start to get more than just equality relationships and transient relationships.
Right. No, that's a very interesting question. So one of the other things that sort of, along with it's not like we're saying there's no backend. There's also still API design that needs to happen. So we're not really asserting a highly specific structure for the query language or whatever you want to describe as the demand. What we're saying is whatever it is, it needs to be composable. But it's ultimately on the API designer to decide what those specific primitives mean within the context of your own architecture. Now, there's definitely some things that I think would be perhaps we wouldn't want to do, we wouldn't want to jump to. So I don't think you want to jump to sort of variables, for instance, any kind of variable binding in your query language. You certainly want to keep it simple and analyzable. But within the constraints that we sort of described under the principles, there's still quite a lot of room for designing your primitives and also just for best practices to emerge because, on some level, we don't quite know yet how far to push it or where to draw that boundary.
And people ask that question a lot. It's actually quite common. And I think, part of our answer is that our intention is not to solve every problem. I think that's unrealistic. People often come out the door and say, this solves everything. And we're not saying that. We're saying by picking a different architecture, we know there's a large class of problems we can eliminate. There may be some aspects of the thing where you're like, oh, we need to include what's the starting index, what's the sort. These things may actually need to be out of band, not in the recursive data structure. You may want to supply that somewhere else. I mean, that really rolls into things like, is this an authenticated request? Which user is initiating this request? There's all this stuff that I think it's dangerous to actually put inside the query language. This goes back to what I said earlier. We don't want to expose something super powerful. We want to expose something that just eliminates complexity. Oh, over.
What's the best practice in fine-grained security?
So we didn't. So again, this is why we showed the JSON graph and the relay stuff. So in Facebook, they do this in a very simple way. And actually, I think their model works for a lot of the applications that people are building, which is that the root of your query is a user, right? The root of the implicit root of the query is who's logged in, and that controls the visibility of what parts of the graph they're allowed to see. Basically, we're saying there's a recursive thing, and that's like a graph, and we traverse that trying to find all the resources. But it's easy because the data structure is simple to say, this person, these are the only edges they can travel. So in DeTomic, again, it's easy. We can actually filter out the database and say, this user can never see this part of the database. But you're right in saying that whatever approach you take, you're going to have to address this problem. Like there are some edges you want to prevent people from walking.
Looks like this implementation resembles OData a lot, and which already is designed for RESTful services and already has a rich query language. So how do you
So it's been a long time since I looked at core data. You're talking about the Cocoa core data, right?
OData.
OData. No, actually, I'm not super familiar with OData. I mean, I know there are quite a few recursive things, but is OData a thing that people actually allow you to run directly on the back end? I'm just not that familiar with OData and what problems it might have. I mean, what is the data that you pass to it? What's the structure of the data? But it's recursive. Is it recursive? So so that if it's not recursive, it doesn't matter, right? Because you need, so the thing that I tried to show in the UI example, if you cannot annotate your UI with this thing, like again, that's the whole trick, is that I can populate an entire UI because the query language itself is recursive and composable. It must have that property. If it doesn't, you're going to be doing lots of weird things. I think that was it. Thanks, everyone.